finding some set stability suspect problems given by Yamakami.
Thank you very much. Well, this is the first talk in the afternoon session, so you might be a little bit sleepy just after the stop the stuff. Well, this talk is all about the constraint satisfaction problems, or simply CSPs. And particularly, I'm interested in the counting version of the CSPs. And also, then I have to put the degree bound here. So what is new? We are going to prove this so-called classification theorem for certain particular set of complex weighted sharp CSPs of degree 2. So I'm going to explain what it is and what exactly they are, and why this is new. This is actually the extension, some of the extension of the earlier result obtained by me about an approximation complexity of the sharp CSPs. But at that time, I was only talking about the CSPs with degree bound of these three. So the two case is unsolved at that time. So I gave some kind of partial solution to the degree two case. I start with giving us a brief introduction about the constraint satisfaction problems. Take a look at the very typical example of the CSP, constraint satisfaction problem, that is SAT. So the instance to the SAT is the logical formula. Well, in this case, I'm thinking about CNF form. And the formula here is the ends of the three ors. I can write down the same formula using a more functional way of writing here. So this is the multiplication of the three or functions. And each function takes the Boolean variables as an output. So we can think of several different kind of questions. Something like the decision version of the CSPs. We are actually asking whether there exists a satisfying assignment for this particular instance. Another version is that counting version. So that we actually count how many satisfying assignments there are. And it is very hard to exactly calculate the total number of satisfying assignments. Then we can possibly approximate that number in polynomial. Another way to look at it in the same formula, we will actually draw the bipartite graph. And the left side of the graphs, we actually attach the variables, and to the right side of the graph, we attach the constraints. So the first question, decision version of the CSP, asking the multiplication of the three ors, that actually lining on the right side of this graph is not equal to 0. Well, that's the kind of question. Another version is that we actually to calculate the total number of satisfying assignments, and that corresponding to calculating the summation of the multiplication of all three ors. So we have seen the structure of the CSP here. More generally speaking, CSPs has.
I have a quick question.
Yes.
Is there a purpose that you're not taking the variables that are complements of?
Here, well, the variables that are not just the labels. Okay. So the or here means so we actually use x1 and x4 and x3. But sometimes we have to make sure that it's order of the variables.
Is there no negation? What about negation?
What's negation?
Negation.
Can you have a bar?
Oh, I see. Okay. Yeah, that's right. That's what you're saying. Well, no, in this case, yeah. Well, particularly this example, I'm not using it. But if you want to negate some variable things, you have to introduce the negation constraint. Right? Here, well, the constraint satisfaction problems appeared in many fields, including artificial intelligence and, say, scheduling problem, the graph theory, and even statistical physics. So that's why there's a lot of people interested in solving the CSPs. still we have an open question of whether we can actually solve the CSP, all CSPs in the polynomial type. So I just quickly go over what the decision CSPs are. Well, decision version of the Boolean CSPs are all NP problems. And particularly, one way to study the CSP is to restrict our interest within a particular kind of constraint. So an F is any set of constraints. And sometimes an F is called the constraint knowledge in some literature. And the decision version of the CSP actually is handled in a set of variables and a set of constraints. But all the constraints are drawn from this particular set F. And the question is, it's exactly the same as before. We actually ask whether there exists a truth assignment, satisfying assignment. So SAT, that's exactly what we have seen. So SAT is an example of the decision CSP, and the color, humidity, vertex, alpha problems, and a whole bunch of problems actually belonging to this decision CSPs. And what is most interesting for CSPs is that if you just make a comparison between the whole entire NP sets and CSP problems. Well, so assuming that the P is different from NP, earlier in 1975, Lautner proved that there are infinitely many distinct levels between P and NP complete problems. This is the world of the whole NP problems. But if you look at the CSPs, the world is much smaller than this whole entire world. But the nice thing is that we only have only two levels. If you look at the CSP, either the CSP belong to is solvable in polynomial time or NP, nothing else. So now we'll take a look at the counting version of the CSP. We just using shorthand notation, sharp CSPs. And the sharp CSP is the problem taking an instance, pretty much the same as before, Boolean variable and constraint. And the constraints are actually drawn for a particular set of constraint F. And now we actually put in the degree condition. The degree here means that the maximum amount of the time that any variable appears among its constraints. Okay, so that's the degree. So that we actually restricting the whole entire constraint satisfy this degree condition. So example of this counting CSPs are sharp SAT, the counting version of satisfiability problem, and the counting version of the bipartite independent set problem, and the counting version of the downside problems. Those problems belong to these sharp CSPs. And as we did before, we just visualize these sharp CSPs. And we have the bipartite graph, and the left side we have the variables, and the right side we have a whole bunch of constraints. Now our task is to calculate this so-called plot. That means the summation over all possible choices of variable, and we actually summing up the multiplication of all constraints that appeared on the right side. And now the degree condition can be rephrased in the following way. So that we actually take a look at it on the left-hand side, and well, this is the graph, so that each vertex has degree. So now the degree, the maximum degree that appeared on this left-hand side of this graph is bounded by D, upper bound by D. So that's a degree condition. So now take a look at it in a very easy case. Well, suppose that we have a constraint that actually taking the variable from x1 up to x sub k. And suppose this constraint can be factorized. Like this one here. So f is factored into u1 up to uk, and all those u sub I is unary constraint. Unary means they only take one variable. So now the f is a multiplication of all those unary functions. In this particular case, suppose some constraints are, well, let's say, in this particular case happens, then f is called the degenerate. So now suppose that you only have the degenerate constraint. I don't care how many. Then the corresponding counting problem, CSP, sharp CSP, that is can be solved in polynomial type and just simply calculate this value. So this is a very easy case. So now we are actually moving into an approximation version of counting problem. So there are several different ways to introduce, well, think about an approximation. So now we pick one particular way of an approximation. So that is the RAS, and randomized approximation scheme. That takes the input of this form. X is the string, and epsilon is the error amount. And then the randomized algorithm produce W. W is a very good approximation of f of x. But now we are taking the relative error, not the absolute error. The relative error means the fraction of the W in f of x is bounded by, well, surrounded by those values. And here is because we are talking about the complex numbers, we have to put some restriction on the argument. So if this scheme runs in the polynomial time, then we call it the fully polynomial time randomized approximation scheme. Important thing about this relative error is that even though the alpha and beta are independently, separately approximate, but that doesn't guarantee that the alpha plus beta is also approximate. So we have to really, be careful about the summation stuff. Now we have to actually measure the complexity of the problem. So to discount the complexity of the problem, we have to introduce the reduction. So here we'll use the so-called AP reduction introduced by Dyers and Goldberg, Greenhill, and Gerard in 2003. This is actually the randomized approximation version of the Turing reduction. So we will use the G as a model, and then to use G, and we will compute F, approximate F in polynomial time. So that's the kind of scheme written here. So in that case happens, we actually draw the notation like this one here. It's pretty much the same as the standard Turing reduction. So they proved that the sharp downset, the counting version of the downset problem is equivalent under this particular AP reduction to counting version of the bipartite independent set. And those are actually reducible to sharp start. It is not known that the opposite reduction of this one actually happens. So now, so we are actually going to approximate sharp CSP. We try to solve this sharp CSP in an approximate sense. And we will actually create some degree restriction. Just take a look at the brief history here. Dyers, Goldbergs, Jasenius, and Richardson, they proved the so-called classification theory. So all sharp CSP of bounded degree are very nicely classified. And I sort of give an extension of their result using the complex degree sharp CSP. But important thing is that their result actually it's only discussed the sharp CSP, so degree bounded by 3. So that this is the minimum degree bound. So that if the degree is 1, then all counting problems are solvable in polynomial. So that the remaining problem is about degree 2. So I give a partial solution to this question. Now, so I'm going to state the result in this paper. Before that, I want to kind of stress that the one particular condition I actually put into beside the result. That is the free unary constraints. So that means I allow any unary constraints for free of charge. So that if you take the input, like variables and constraints, but then you can always add extra unary constraint without thinking, without charging anything here. And for example, the unary constraint of the Boolean values are, a typical one is delta 0 and delta 1. And that's actually computing that x is actually false and x is true. And this particular condition or assumption is not really new, and a whole bunch of people listed here, they actually use this assumption. Because using this assumption is to make the argument simpler and clear. Now, I want to explain about the symmetric constraint. The symmetric constraint is the constraint whose output values are depending on the Hamming weight of the input bits. And that means the value of the f depends on how many ones you have. So for example, 0, 0, 1, 0, 1, 0, 1, 0, 0, so you only have 1, 1. So in that case, all the values here are exactly the same. The same way, if you have two ones, the value is the same. Well, the graphically speaking, so we simply to change the order of the variables. That is exactly what we did there. If the constraint is not symmetric, then we'll call it asymmetric, right? And the one example is here. So if you have multiplication of or like this one here, so this is symmetric constraint. But if you are actually missing the last one, so this actually gives you asymmetric. So asymmetric constraints are very hard to handle. So one way I came up for this paper is that symmetrization. So if you just split transform from asymmetric constraint into symmetric constraint. And the way I did is that, so look at this one here. So you just place the f in the triangular form, and then just to put that input. So an obtained constraint is always symmetric, no matter what constraint you get. So earlier in the time here, they actually introduced a very important set of ternary symmetric constraint. So I call it Sing 1 and Sing 2. And the definition is written here. And if you apply this symmetrization, then the distinction between the Sing 1 and Sing 2 are very clear. Because if f is from Sing 1, and then you apply the symmetrization, then it becomes just a degenerate. But then the second case is very different. So now, so I introduce one more notation here. It's an f sub sigma. So that means sigma is the permutation over 1 to 3. So that we actually permuting the order of the variables here. And now I introduced four set of constraints. The first one is the big one here, and the last three of them are actually the partition of this sigma set. And if you just carefully look at this one here, then for any permutation, and symmetrized version of f is not degenerate. If this is true, then symmetrized version of f is either Sing 1 or Sing 2. Now, I introduce one more set of constraints here. So, if you just take a look at the graph like this one here, if f can be, f belongs to DUP, this represents a duplication. So if f belongs to DUP, then f can be factorized into two functions. One of them has to be unary. But this is the last slide here. And finally, is I reached my result here. And I got the two theorems. And theorem A says if F does not belong to SIGC, then, well, the corresponding counting problem is sharp E hard, harder than the sharp SAT. The second theorem says, so now we are looking at the part of the thing, so the thing 1. Then we only have we got the dichotomy theorem here. If F belongs to DUP, then well we can solve sharp CSP in polynomial time. Otherwise, this problem is sharp E hard. And we only discussed the thing 1, some similar ideas and works for the thing 2 and thing 3. And then the other proofs will be published shortly. Thank you very much for listening.
One very quick question. Yes.
I know you didn't go into too much detail on the technical aspects of your work, but do you think that your technical contributions would be useful for finding approximations for other sorts of Holland problems as well?
What kind of problem?
Just other settings of Holland problems rather than this degree 2 CSP thing, but other types of problems in the same area. Do you think that would be useful?
Yeah, I hope that. Yeah, well, I haven't tried it in this game yet, but possibly we can use this kind of instrumentalization, but not necessarily